Okay, good morning. We continue the lesson. So the next lesson is actually understanding a little bit, not understanding, knowing a little bit the form of the graph of the trigonometric functions, yes? So we want to see that, okay, for example, if I tell you y equals to x squared, you have a rough idea how the graph of y equals x squared looks like, yes? So everyone knows probably that the graph is a parabola like that. So we want to have the same more or less understanding about the graphs of trigonometric functions, starting with sine and cosine. Tangent is a little bit more difficult. Why do you think that this is the case for the case of tangent? Yes? Now, why do you think that the graph of tangent should be a little bit more complicated to discuss? Yes?
Isn't tangent not defined in some situations?
In some situations, because tangent is actually a fraction, and then when sometimes the fraction, the denominator, which is cosine, vanishes, and then we have some problems there. But for the case of sine and cosine, I don't have any limitations at all for the values that I can put instead of x. Yes? So today's lesson, we want to talk about y equals to sine x and y equals to cosine x functions. So most of the time we want to use Geogebra to understand this a little bit better, but we can also understand it. Let me just try to understand it using the traditional way of whiteboard and pen, and then we go back to Geogebra to see better pictures there, to have a good intuition what's going on. Okay, first of all, let me just concentrate on one of them for the time being. Yes?
Are you recording this screen?
Yeah, I have changed my style now, so that's always you see this, but I have some control panel in front of me, so that's working fine, hopefully. Okay, so, but that's very good that you reminded me, thank you. Be observant always. So one question, what is the domain? Let me talk about the domain of this function. What is the domain of function sine x? What do I mean by this question? I mean, what are the acceptable values for x that I can put in and still get a number? Or other words, do you see any limitations for the value that I can choose for x? Yeah, so if there are no limitations, so it means the domain of these two functions are x. If you take your calculator, punch any random number for x and calculate sine of that, you will get something. So it means sine x is defined at all possible values, okay? So the domain of these two functions, the domain is R. This is something that you need to know. So you should expect that the graph is extended on the whole real line. By the way, this is also sometimes a matter of confusion. What is the domain of this simple function y is equal to x squared? Is there any limitations for the value that I can choose for x? No. So the domain is still R. But do you think it's extended all on the whole real line? Yes or no?
Yes.
Yeah, it should be. Even though it's a little bit counterintuitive, yes, you might think that this is not actually covering these parts on the real line, but it eventually will cover. That's the whole point, yes? If you say it will not cover here, for example, let us x equal to 1000 here. If I take x equals to 1000 and put it here, it will give me 1 million. So it means 1000, 1 million is a point on this graph. So it means that eventually this graph will actually pass all the points. So this is the counterintuitive way. So don't think that this will not cover the whole real line. It will cover the whole real line. Let me just repeat. Do you think it will cover the whole y values? It is clear no. There is no returning back for this. So the negative part is completely uncovered. But from the x point of view, it will cover every value. Okay? So you should also expect something like this happening for sine. So if you see the graph of the function, you should be able to understand that this will cover the whole x-axis. But what about the y-axis? Let me ask your understanding before me doing it. What do you think? Do you think that the graph of this will also cover the whole part of y? Yes, Ricard? Yeah, so everything should be between -1 and 1 because we learned sine and cosine are maximally 1, minimally -1. So they will be very limited in the y range, but in the x range, they will go from -infinity to infinity. But there is a feature that these two functions have, this function lacks. And that is these functions start repeating themselves over and over again. And that is the notion of the period. So for example, if I ask you, what is the value of sine x plus 360 degrees more? The answer is the same as sine x. Yes? Because if I add 360 degrees to this x, I will return back to the same point, so the value of sine remains the same. So this is called the period of the sine function. What does it mean? It means that at each interval whose length is 360 degrees, the function starts repeating itself. So this means that even though the domain is R, and in principle I should draw the graph of the function on the whole real line, but I don't need to do that. I just need to concentrate on one interval whose length is 360 degrees and draw the graph there, and then take that part and copy and paste it over and over again from left and right. This will generate the whole graph. So working with periodic functions are actually a little bit simpler. Instead, rather than going through the whole domain, I just go through one period, draw the graph, or understand the function at that period, then I will be able to answer the questions related to the functions when I am outside that period. So is that clear? Okay, and then if I ask you to tell me an interval on the real line whose length is 360 degrees, might be the natural choice is to start from 0 to 360 degrees. You could equivalently start from -180 degrees to 180 degrees. That is also 360 degrees, coverage of 360 degrees. But the most natural one, hopefully you agree with me, I want to understand the graph of the function where x is only between these two values. Why? Because if I know the graph here, because my function is periodic, I take that part and copy and paste it over and over again. Okay, let us try to understand that. By the way, to understand the graphs, you need the notion of derivative, which will be the topic of the next chapter. So to understand the maximum points, minimum points, and things like that. But here I'm just talking qualitatively, because I want to rely on GeoGebra, okay? So here, let us take x, and let me take sine x. Because I don't have calculator with me, I just stick to the values that I can do it in my head, and they are simple. If you look at your book, you see that they have more numbers for this interval. I only choose 0 degrees, and then 90 degrees. The book has also chosen some intermediate values between them. And then I go to 180 degrees, and then I go to 270 degrees, and then finally 360 degrees. I think that would be enough for our purpose here. So if I replace x in this function with 0, sine of 0 degrees is 0, sine of 90 degrees is 1, sine of 180 degrees is 0, sine of this one is -1, and this is also 0. Okay? Of course, this will give you a rough idea how the graph looks like. Okay, so for example, assume that this is 90 degrees, and this is 180 degrees, and this is 270 degrees, and finally 360 degrees. Okay, let me change my color here. So 0 degrees, the value of the function is 0. So this is one point which definitely lies on the graph. But when x is 90 degrees, the value is 1. So because the units are different, so it doesn't matter scaling here. So I put 1 here. Okay, so by the way, let's stick to the correct colors. So this is 1, assume this is 1. So if this is 90, it is 1. So this is 1 point on the graph. 180 is 0. That is another point on the graph. 270 minus 1. So if this is 1, the same amount going down, this gives me minus 1. And then this point is also another point. And finally, 360 degrees, I return back to 0. So then, if you want to draw the graph, of course, there are infinitely many possibilities. Should I go like this? Should I go like this? If I want to answer these questions rigorously, we need to know the notion of the derivative. But trust me on this, so the graph will look like this. Yes, if I can draw it, but it doesn't matter. You will see the real graph on GeoGebra. Something like this. It is like oscillating wave. So this is why in physics, when it comes to waves, it is important to know about periodic functions like sine and cosine. Okay, but is this the whole truth? No. This is not the full graph of sine x. Okay, this is just the graph of the sine x in one period. The length is from 0 to 360 degrees. Then I have to take this as a rigid object, for example, and just translate it, shift it to the right and left infinitely many times. Yes, so that will give me the graph of the function like this. Yes, something like that. So that's the graph of the sine function. I can set up another table, and it is instructive to have both of them in one coordinate system to compare them. But before doing that, can you tell me do you expect a big difference between the graph of sine and cosine? If not, why not? Yes?
Well, when x is 0 for cosine,
No, you are talking numerically. No, conceptually. Why you shouldn't expect a surprise when you are doing the graph of cosine?
well, the maximum value is 1 and the minimum value is 1, and therefore it also,
No, the minimum value is minus 1 again.
yeah, and
Yes?
therefore it also is in the same.
No, and one more thing, it's also periodic.
Yeah.
It's important, and the period is again 360 degrees, not less. Yes? This is one thing, that's good. Another explanation is that the sine and cosine are actually the same quantities. They have been actually, so the sine of an angle is equal to the cosine of its complement. So you shouldn't expect that much a difference. So even if I'm talking about cosine, you can write it as cosine of the complement, sine of the complement, and we already know the graph of the sine. So the graph of the cosine should look very similar. And indeed it is. Let us try to set up another row for this table here. But this time, I want to continue with the values of cosine. If I put 0 degrees, cosine of 0 degrees is not 0, is 1. But cosine of 90 degrees is 0, cosine of 180 degrees is minus 1, cosine of this number is 0, cosine of this angle is 1 again. And if I change my color to draw the graph here for you, so what happens here? If I have 0 degrees, the value is 1. So this is a point on the graph, not this one. But if it is 90 degrees, it is 0. So this is another point of the graph. If it is 180 degrees, it is minus 1. So I have to go down. This is another point. 270, it is 0. And this is again 1. Okay, now I draw the graph. Something like this will happen. Something like this. This is the graph of the cosine in one period. But then I have to take this green part and copy and paste it over and over again. So what will happen? So I will have this situation. I cannot draw it perfectly fine, but you will see the real graph in Geogebra. Yeah, it is better to draw it with dashed lines, yes, because as I did with the sine function. So, but you need to do it. It doesn't mean it is not part of the graph. It means that I am just imagining what will happen. And I hope that you agree that they are actually carbon copy of the same thing if you consider them as rigid objects. One of them is being shifted a little bit to the right or to the left. Okay? Of course, you can shift it even more, but the minimum shift is this length. Yes, I can shift even more because I can shift, I don't know, this is 90 degrees. If I take the green curve as a rigid object and shift it 90 degrees, this length to the right, then hopefully you agree with me, it completely overlaps with the blue one. But of course I can shift more, but the minimum value of the shift is 9. That's the representative of what I said. The sine of a function is cosine of its complement, and vice versa. So that 90 degrees shift is actually visible here. And then again, you see that the graph touches this line at some points. So it reaches to maximum 1, but it is mainly below 1. And it also touches this -1 at some points, but it's mainly above 1. So it is actually limited in a narrow strip, yes? It's between -1 and 1. So this is something you have to have in mind. So now you understand this wavy behavior is very suitable for talking physics when you are talking about waves similar to this. Okay? Any questions? But now let us go to GeoGebra here. In this case, I'm not sure you can also help me to do that because it is good for the exam to be able good in these things. So first of all, if you don't mind, let me get rid of these very minor lines here. So what should I do? Well, I should only major guidelines. And then let us see what happens if I type to draw the graph y equals to sine x. This is the graph. That was, actually I spoiled the joy of the problem. Could you anticipate that this will pass through a little bit above 3? Because this is the graph of sine x according to GeoGebra. And by the way, if you just let me to turn this on. Yes, and then come back again. Okay, so here, could you anticipate that the graph will pass close to 3 here? Anyone else? Yes? Why?
Yes, you could.
Yeah?
Because that corresponds to the point pi,
Uh-huh.
and pi is kind of equal to 180 degrees when we're comparing radians and degrees.
Yes.
And we know that at 180 degrees, sine x equals 0. And
Yes, so
we
it means that if I come back here, what you are saying is that this blue curve is passing through 180 degrees.
Yeah.
This is the first time that the sine function intersects the x-axis on the right-hand side. That is 180 degrees, which is equivalent to pi radians, and pi is 3.14 something. Be careful, don't get confused. You shouldn't expect that this is going to close to 180, as I told you before. Pi is 3.14, so it's very close to 3. So this is why you see that this is actually possible to predict that it is passing. Why? Because GeoGebra by default is doing in radians. And this is something that I don't know exactly about GeoGebra, how to change the default setting, but I probably can do something here. Okay, so let us go back to GeoGebra. So here, let us try to see what we can do. Let me just to see if we can do it in degrees. If I remember correctly, so if I go to graphics and then I go to x-axis, I can take the distance. I think 45 is good, so let me make it 45. And then let me change the label to degrees. And then the problem is that what happens now? I go to, so I can imagine what is going on, but not perfectly. So this 45 somewhere, okay, so this is in degrees. The distance I want is 45. And then the point is that I have to rescale it as well, I think. So if I go to this scaling, make it 50 to 1, and then this strange thing happens. And then now you see that there's 45 degrees, but okay. can you tell why this is happening? Why this strange behavior is happening here in the graph? That's also a good question. So if you want, I can zoom in. I don't want to destroy it, but you see that I have a lot oscillations going back and forth, which is probably not intuitively according to my picture. The reason is that, yes, the reason is that still GeoGebra is working in radians. Okay, so it doesn't care about the distances, whatever it is actually considered. I just by default put a dot on it, but it is considering 45 radians. Yes, and 45 radians is a very big number, so we have more oscillations. So the way that I could solve that problem, I think once I went here to f of x, and I chose this degree sign. So you go here and then change it to degree. Hopefully this will fix the problem. It didn't. No. It should. Yes, it is working. So now this is the way. I don't know if you can find a more efficient way to switch back and forth. I think it should be possible to just say to GeoGebra, from now on I am working in degrees, from now on I am working in radians. I don't know. If you find it, please share it with me as well. But that is the graph for the timing. By the way, degrees is very confusing for me. Might be radian is confusing for you, because I have learned to think about actually radians a lot rather than degrees. But anyway, we were able to adjust this on radians, okay? And then what I do, let us just draw the graph of cosine as well, but for the same form. So I would say y is equal to cosine, and then you write x, but you shouldn't forget about exactly the same thing happens, because this is in radians now, and then I have to put this one and then plus the inter. So you see that this red one is actually, the red one is cosine function, the green one is the sine function. I hope that you agree that this is the same actually, except one of them is being shifted version of the other one. Yes, please.
How would we shift the cosine x so it overlaps entirely with the sine x?
So you can answer it yourself here. So how much shift we need? For example, consider this red curve as a rigid object, and the green one also as a rigid object. How much I need to shift along the x direction so that the red one overlaps with the green one? It is clear. 90 degrees. Yes, that's clear. Any questions here? Okay. Another thing that you need to know, according to the problems in the book, I will not give you these kinds of questions in the exam to solve a problem graphically, but by the way, it doesn't mean it's not important. It's actually extremely important. So sometimes you need to be able to solve equations graphically, which in this part you have a lot of exercises. Yes, just let me close it. Okay, so now the point is that, by the way, I told you that in the national exam you have already the experience. There are questions design that you have to use. Even if you have very good analytic skills, still you cannot solve them. Yes, you have to know how to use applications effectively, which is, of course, is very important. So this is why let us try to solve some of the problems, and then you're finished. So one problem is, for example, you want to solve this analytically, or no, sorry, graphically. So they give you an equation. We already know, by the way, how to solve this simple equation analytically. But let us assume that I want to solve this equation graphically. Sine x equals to 0.3. Okay, so let me go back to GeoGebra. And then, for the time being, I get rid of cosine. I don't need it. I keep sine. Okay, can you tell me what to do? I want to solve an equation graphically, not only for this one. We have already talked about this, if you remember. I have already talked about if you want to solve this equation analytically, graphically, what is the general strategy for any kinds of equations, not just trigonometric equations? For example, you want to solve this polynomial equation. So what can you do? Do you have any idea? We had this before in Math 2, yes?
You mean
In GeoGebra, for example, of course, GeoGebra is capable of giving you the analytic way, but assume that you have only graphical tool in your hand and you want to use it somehow, yes?
well, then you could put in y equals x to the power 3 plus x to the power 2.
Okay, so what you are telling me in words, it means that you draw the graph of this function and you draw another graph for this function, then
And then on the point where they
intersect, and then
you check the y coordinate.
No,
sorry,
the x coordinates. That is the point. So you find the intersection points between these two graphs, and the answers to your equation are the x coordinates of the points of intersection. This is one way of doing it. There's also another way. Sometimes it is preferable. Because here, on the left and on the right, I have two curves that are intersecting, yes?
Could you possibly make it into one function?
How?
And then see the
How?
Oh, you take the left-hand side and move it to the right.
Yeah, so if you move it to one side, it becomes a new function. So for example, this becomes x to the power of 3x squared minus 2x plus 7.
Yes.
And then you draw the graph of this one. On the right-hand side, 0 is left, so you still draw the graph of this one, but the graph of this one is already drawn in your system, that is the x-axis. And then look for the intersection with the x-axis.
Yeah.
Okay, but according to the book, they are using the first strategy for this one. We can also solve the other way around, it doesn't matter. Okay, by the way, we can check both of them here. Okay, so let us go back here. So I already have sine x degrees here on the GeoGebra. So what I have to do, I have to write y equals to that number, 0.3. Okay? Okay. So on GeoGebra, which I think it's better to know, is that there is some instruction in syntax called intersect. But by the way, so what do? I choose this one, and then I highlight the graph of this one. And then what do you think will happen if I highlight the second one? Yes?
It will find the intersection.
Okay, but do you think the computer is capable of doing it?
Yes.
No.
Why not, or why yes?
Because it's like
Infinitely many. So the computer cannot calculate infinitely many, so there is no algorithm. You have to wait infinitely many hours, yes? So I think GeoGebra will actually solve the problem so let us just not anticipate that. Okay, for example, let me start here. Okay, it gives me this one. Or I think if I now use the same thing, okay, it was already chosen, and then I just click close to this point, yeah, it is probably, this is the way that it works. So if you are interested in any one of these points, you have to click close to it, okay? But if you don't mind, let me just delete this b for the time being. So this will give me a. And let me just go to the positive values, okay? So I will choose this one again and that one. And let me just choose one more on the positive side. I get this one, okay? And the numbers you see here, the values, I have set the GeoGebra onto 2 decimal points, so it is keeping only 2 decimal points for me here. Okay, so can you just by these numbers write the answer? So one of them is 17.46. What is the units here? What are the units? Degrees here, because I set my system in degrees. So this is 17.46 degrees. This is, I don't know, 162.54 degrees, and etc., etc. Yes? So how should I actually write the answer? So how do I write the answer? So I would say that x is equal to, what was the first number? The first number was 17.46. Plus, what should I write? N times 360 degrees. I hope that you agree with me. You shouldn't expect that this one single formula generates all the values, because If I give 0, it will generate the first value, but if I give you 1, it suddenly generates something beyond 360 degrees. But you see in GeoGebra that there is something before that. So that is exactly what we know about sine. Do you remember the other scenario was 180 minus that number, and now you see that 180 minus this 17 point whatever is 160.54. So this is actually predictable. Okay, so what I mean, so we can write the other scenario, x equals to 162.54 degrees plus m times 360 degrees. So sometimes GeoGebra it also helps you. If you have a graphical tool in your hand, you should be able to solve that problem. Any questions? So they are very simple actually. But I think from the experience that I had from your last national exam, it is also better to address these questions using computers. It's important because that will be one part of your exam in the future. Okay. Do you want to test the other idea, by the way? So let us go back to GeoGebra. So try to get rid of these things. Delete. Yes, good. And then I will actually draw the graph of this function. By the way, before drawing that, that would be the next lesson. I will talk about it. But can you predict what will happen if I take this one? Do you remember? I want to use the second strategy here. Because one strategy was to draw the graph of these individually and look at the intersection points. One possibility was to move everything to the left and consider the intersection point with the x-axis. Now I am trying to understand the same problem, but from the different perspective. But before doing it using GeoGebra, what will be your prediction? If I press enter here, what do you think will happen to this nice green curve? Yes?
Technically, you would just lift it down by 0.3.
Yeah, because what is happening, if you see here, what is happening, if I move this to the left and write y equals to, this is, by the way, I will talk about this systematically. That is actually the important part of this lesson, which will come for the next lesson. But if I draw this, what is happening? Whatever I put for x and calculate sine n, in order to calculate y, I have subtract 0.3 from it. So what happens, every y coordinate will go down by 0.3 units. So the effect will be like this, that I am taking this rigid object and shifting it downward by 0.3 units, yes? Okay, let us just do that. Press the enter, I go to GeoGebra. This happened, yes, actually it happened, yes? It is a little bit lower now. But now in this scenario, what I'm supposed to do? I am supposed to find the intersection of the curve with the x-axis. I can either use that one, but I think there's also another one called zeros. Do you remember where it is? I think I saw somewhere about zeros of a function, yes. So here, okay, roots. Let us check roots, let us see what is going on. Let me check roots. Yes, so the roots is actually, it is clear from the icon that this is the intersection with the x-axis, but still GeoGebra will not be, okay. Actually, it's a little strange. It is giving us, probably in this limited display range. That's better. So this means that in GeoGebra, this works better, yes, in order to click every now and then, but you can find all of them in one go, yes? And then again, hopefully you agree with me, this C, you shouldn't be surprised, because if you read the coordinates of C, is 7.46 is exactly the same number we got from the previous method. Yes? So now we learned something. Using this is more efficient, yes, than the other one. Okay. By the way, let me try to solve a little bit more complicated problems, yes? And then we can also solve it analytically, and that would be the end of today's lesson. Let me go back. I really enjoy this creativity of mine, yes? So because I am not disturbing you by switching the cameras, hopefully everything is working. Okay, now let us see So this is the question. We want to solve this problem graphically and analytically. Yes, that is also good to do it analytically. So sine x equals to cosine 2x. Yes. Should we do it right away in Geogebra? Might be that's a better idea. So let me just get rid of all things we have. Delete and then, okay, so we can follow both the strategies, yes? So for example, I can write y is equal to sine x, but I have to go here and put the degree on top, yes? And then I also draw the graph of y equals to cosine and then 2x. So let me put a star here, I don't know sometimes. Oh, I have to, by the way, you remember you have to put these pair of brackets for cosine. Otherwise, it actually consider it as a variable. Okay, so this is the graph of the second one. By the way, we will understand why. Might be if I ask you before, you shouldn't be able. Could you anticipate this will be the role of these two? Because this orange one is not cosine of x, but it is very similar to cosine of x. Can you see the big difference between the graph? This is the future lesson. I just want you to see a little bit ahead. So what is the difference between cosine of 2x degrees and with the cosine we had? Yes, Robert?
The period is small.
Yeah, it is squeezed actually. Even though I am multiplying the x value, but you can feel that it is squeezed because now you see that the period is no longer 360 degrees. You see, from here up to here is one period, and the function is repeating itself after that. So the period was 360 degrees, now it is reduced to what? 180 degrees. We will speak about them systematically. But again, probably if I want to find the roots in this way, I should go here and go to intersection. Let us consider this point first, this one and that one. So this is my point. By the way, it is just exactly 30 degrees. It's good. So this point is 30 degrees. And then let me just go here and there. This is also 150 degrees. By the way, this should be able, you should be, I don't know if you could be able to predict this one or not. So again, I have another intersection. Let me just consider everything on top of the x-axis first. So that is C. So these are some points that I see, but there are also some points that these two curves touch, do not cut. Yes? For example, let me consider this close, and this is my D, and these are the angles. Okay, I don't know, by this observation, without doing analytic work, can you write the formulas generating all these points? Might be you are able to write one formula, two formulas, or three formulas, but you should be able to actually convince yourself that you're considering all the points. So what should we do? So you see, point A is 30 degrees. Point B, you see, read it here, it's 150. And point D, what's happening to point D, is 270. What happens to point C is 390. And I hope that if you agree with me, I can go to the left-hand side, the pattern will continue. But can you see a pattern here? By the way, it is very strange for me now, because I didn't expect that I can generate all points with one single formula. Can you see that you can generate all these points with one single formula? So 100, so here, just let us review again. A, look here, 30. The next one, B, is 150. The next one, which is below, what we don't care about, the y value, we care about the x value, it's 270. And then I go to the next one, it's 390. Yes?
The difference between all these points is 120 degrees.
To be honest, that is not what I expect. So sometimes graphics is good because our brain is more designed for shapes than abstract things. Okay, or evolved in that way. So apparently this shows, I will try to do it analytically, now this is exciting. So this tells me that all these points of intersections can be generated with one single formula. Okay, let me go back to camera. Can you write that formula for me? Can you write the formula?
Is it,
Because in principle, this is the topic. You need to do graphically without analytic calculation. By the way, this is important. They can give you questions that even I myself cannot solve them analytically. And you will get those questions definitely. So it means that they force you to use GeoGebra graphically and then try to answer them analytically. Yes?
is it x equals to 30 plus 120 times n?
N. Thank you. So this is also my expectation from what I see in front of me. So you said 30 degrees plus 120 degrees n, where n is an integer. This is our prediction, which was a little bit counterintuitive for me because I can see analytic solution. So let us see how it works. So this is this way of doing it. And by the way, let us try to do it in different way. Move this to the left and try to do it once more, if you don't mind. So I go back to GeoGebra, and now let me take here, let me clean everything below that, I don't need them, but then I would say that minus cosine this 2 star x, and then I would press this degrees and then enter. Okay, it's a nicer object. It's like sound waves, yes? By the way, they are true because there is a theorem, by the way, it's a very important theorem in mathematics called Fourier Theorem. He actually showed that any function, let us for the time being keep it periodic function, can be written as a composition of only sine and cosine function. So it doesn't matter how odd the form is, but this is always possible. But anyway, this is the graph you have. If we learned what to do with GeoGebra, so we go back here to find the roots. And then let me click here. Yes. So it gives me these roots. And then you see that this is 30, 150. And by the way, let us test this idea. It's curiosity. Okay. As far as I move here, it's generating points. Yes, that's good. We cannot cheat it. Yes. Okay, anyway. So this formula, probably what you have written for us, and the formula is correct. Yes?
But this skips the point 2.
What?
It skips.
Yeah, that is also, yes, you are right. It is a skipping. Yeah, that is good observation. That's good. Let us go back here. What actually Gustav is saying is that these are also solutions, but for some reason GeoGebra doesn't detect them. Yes, because do you agree that this is touching? It's always probably finding, according to this, only cutting points. But you can also ask GeoGebra to find extreme points. But this is a little bit cheating, yes? So I can use this and then probably press on that. But of course, this is not good because this is no longer a solution. So let us just undo that. Yes.
Could you possibly use the roots setting?
Where was roots?
I think it was there.
Here?
Yeah.
So I used that one. I don't know, for some reason, as you mentioned, I didn't observe that. It is keeping these two. These are roots as well.
Yeah.
Okay, these are roots. I want you to understand them, even though GeoGebra is not showing them to us. Okay, those are roots. Okay, so the formula seems correct. But let us go back to solve this problem analytically. Now assume that you are in that part of the exam that you're supposed to do it analytically. Now tell me what to do. It's interesting because I want to see what will happen if I solve this analytically. How do you think about the problem? You want to solve sine x equals to cosine 2x analytically. Yes?
Can we rewrite it to sine or cosine?
Okay, but how? No, because which part of the formula sheet you will go and look for? Because there are many formulas, 5 pages, 6 pages. So which part of the formula sheet is suitable when it comes to solving this problem? You need to remember a word or something about the topic of our lesson. Yes?
Was it? I forgot what the formula was called and exactly what it was, but since cosine 2x.
Yeah, that is called the double angle formula. So you need to go and look that part of the formula sheet which is related to the cosine or sine of the double angles. And then there are three formulas for cosine 2x. So I will write all of them. You tell me which one is more suitable in this context. Yes? So the formulas, let me write them in blue. The formulas are cosine 2x equals to cosine x squared minus, this was the standard, this is the original one. But from here, I derived two more. This is a mixture of sine and cosine, and I wrote one formula which was only in terms of sine, and I also write another formula which was only in terms of cosine. But for the purpose of solving this problem analytically, which one of these three is more suitable? Yes?
Can't you use the supplementary angles, the complementary angles for this too?
Yeah, that's also good. Yeah, we can also solve it in that way. We can compare. We have a lot of things to do, okay? So that's good. We will also do that. But for the time being, which one, if I want to use, is suitable? Yes?
1 minus 2 sine.
The middle. Yes, because if I use this, still I will have a mixture of sine and cosine in my equation. If I use this, I have cosine on the right, sine on the left, still I have a mixture. Yes, so this means that I have only, it's better to use the middle one. Okay, by the way, that method that Gustav also mentioned is actually very good. So it means that this could be, I could have asked this from you even if you don't know the double angle formulas. But anyway, let me just use that one. Instead of this, I would write sine x equals to 1 minus 2 sine x squared x. So then I hope that you immediately realize what to do. What should I do here? Yes?
You move over the 2 sine.
And the idea is?
You factor out the sine.
No. Factoring out doesn't work, yes?
Should we use ABC formula for this?
Yes. So that means that we have to, the auxiliary variable or something like that. So I move this to the other side. So this becomes sine x to the power of 2 plus sine x minus 1. If you want, you can immediately start ABC formula if you understand what's going on. But if you want to be a little bit more relaxed, you can say this is not compulsory, by the way. Introducing auxiliary variable is not compulsory. That is for your comfort. So I would say let capital X be sine x. Then what happens? This equation will read 2 capital X squared plus capital X minus 1 equals to 0. And then, of course, I prefer to use ABC formula, so the capital X is equal to minus b, which is minus 1 plus or minus a square root of this number to power 2 minus 4 times this times that, which is positive 8. And then divided by 2 times this number, which is 4. So the answer becomes minus 1 plus or minus 3 divided by 4. And then I have two solutions, yes? One solution is negative 1, because minus 1 minus 3 divided by 4. Another solution is positive 1 half. This is, I could anticipate this is coming. This is why it was surprising for me that we can combine all solutions into one single formula. So that was a little bit counterintuitive for me. So that graphical tool helped me to understand this. Okay, but hopefully I can prove this analytic to you. We can discuss together. I don't know what's going to happen. So I will have x equals to minus 1. Then what happens? It means sine of little x is minus 1, and then I want to solve that problem. I told you for the cases of 0, 1, and minus 1, even though you can use those formulas, but don't distract yourself, you need to actually understand it. This is faster. It doesn't matter if you want to use the formulas that I told you during the lesson. Where sine x is minus 1, sine is the y coordinate. I want to have the y coordinate minus 1, so that is just one single point. So this point is minus 90 degrees. So the answer becomes what? 360 times n. Do you agree? So n belongs to Z. So that is one part. This is why I'm telling you it was counterintuitive, yes, because I will get two more from here. Yes, because x is equal to 2, x is equal to 1/2. This means that sine x is 1/2. And then we have two options again. Little x is equal to sine inverse of 1/2. But let me calculate. Sine inverse of 1/2, I have it in my memory. It is 30 degrees. And then plus 2m pi. Not 2m pi. I should stick to radian or degrees. So it is 360 degrees. M times 360 degrees. Or, what is the other scenario? Can you tell me? If one of them is 30 and the case is sine, the other one is
150.
150, yes? It's 150 degrees plus another letter, for example, p times. It doesn't matter, by the way, to change the letters because they are not supposed to happen simultaneously. So m and p belong to z. So you see I have three formulas. That's what I'm saying. To be honest, if I wanted to solve this problem, I will let it go like this. I couldn't anticipate that I can combine three formulas into one single formula. So that's why I'm saying that if you leave it like this, that's completely okay. But just as a matter of curiosity, of course, if you are smart enough to see that this one single formula serves for all three cases, that would be much better because I can just write it very compactly. But how can I understand this? I already told you, I already provided you with the tools so that you can understand this. How we should understand that? How can I understand that the formulas can be combined? We have to go to the unit circle and see how many points are there. Because what matters is that the points. So if I go to the unit circle and I ask you where there are infinitely many angles generated by this single formula, but all of them represent this single point. Yes. What about this? This is 30 degrees. For example, this is 30 degrees. All of these formulas generate one single point on the unit circle. 150 is exactly here. So this is another point. Now, when you draw the picture, it becomes clear that you can combine them into one single formula. Why? Because if I start from 30, if I just go 120, this is 120 degrees, by the way. But how many degrees is here? This was 150, this is 270. So the difference is still 120. And this is 270, this is 30 degrees more than 360. It is 390. So again, this angle is 120. Now it becomes clear that this really works because you can combine all the formulas here. So I start from 30 degrees, but instead of going one full round, I go 100 degrees, I reach to this. I go 100 degrees, I reach to this. And then I go 100 degrees, I come back here. So this means that it is clear that I multiply this just by 100 degrees. So even from analytic point of view, that was clear. But if I wanted to solve this problem, I would just leave it like this with three formulas. And so that is good that sometimes you use graphical tools to improve your understanding. If you don't mind, we don't have that much time, let me solve that problem using what Gustav mentioned. Hopefully, let us see if there is other surprises here for us. So what should we do here? If I want to solve this using what Gustav mentioned, for example, I decide to keep sine, but I change cosine to sine by the famous method of complement angles. Yes? And then I give the role of box to this and give the role of the circle to this, and we know what happens between these two. Either these two angles are equal plus n times 360 degrees, or the one in the box is 180 degrees minus the circle plus say m times 360 degrees. Okay, let us do some calculations in our head. I move 2x to the other side. It becomes 3x. And I divide everything by 3. So then it becomes x. This becomes 30. And then this becomes 120. So this method is superior here. Yes? Because it actually exactly gives me the proof. But of course, there is another thing coming up. We have to convince that these two are also can be combined. So this is exactly one answer that we were able to find after so much suffering, yes? And then so what happens here? So this becomes what? 180 minus 90 is 90. And this one plus, it becomes plus. And then I move this to the left. It becomes minus x equals to 90 plus m times 360 degrees. But then I multiply everything by a negative sign. I take this away. This becomes negative, and this also becomes negative. But you might think that there are two solutions. But they also can, this is also covering this. Do you agree? Because if I ask you where this point is located, this point is located down there. And then this not only covers these 2 points, but also this one. So when it comes to the competition between these two, this will win, so I will keep that one. But still, it was a little bit better because we didn't have any 120 coming from here, but at least we see 120 coming from there. Okay, so I mean, the good point about mathematics is if you do them legally, in the world of mathematics, the answers are always consistent, so it doesn't matter what you're doing. Okay, so any questions? Okay, so I will stop actually here. I don't know how much time we have, but let us just stop here. No questions?